share a screen because I want to review some material about diatomic molecules. So let me get going with that. Share here. Oh, plugin, it says, okay. I think I install a plugin every 2 or 3 times I do this. All right, let's get this going here. Let's enlarge it. Let's lock it in. Okay, good. Yeah, so let me start a few minutes early just to review where we ended up last time. So we're dealing with diatomic molecules, and I took for numerical work, I took the case of the carbon monoxide molecule. I wanted to have a diatomic that didn't have hydrogen in it because hydrogen's got such a small mass. It kind of imbalances the mass formulas. But anyway, you could take a diatomic with hydrogen, also H2, for example. The potential is sketched over here, which gives you a qualitative idea of what the potential looks like between the two atoms. The force is strongly repulsive at short distances. And this is, excuse me, I just got a message that said participants can now see your presentation. Does that mean that a moment ago you could not see it?
No, we
Anybody?
could see it. I could see it.
You can see it? Okay, I don't know why it gave me that. At short distances, the force is repulsive, and it's really electron degeneracy pressure. You're trying to cram 2 electron clouds from the 2 different atoms on top of one another. At large distances, the force is electrostatic, and it's caused by the mutual polarization of the 2 atoms between themselves. In between, these 2 effects compete with one another to give you a potential well, and with a minimum at a certain radius. So we call the depth of the well minus V naught and the radius R naught. These are 2 basic parameters of this curve. Now, there's no simple analytic formula for this curve, and it's not the same for different diatomics. It's different for, depends what the atoms are. But the qualitative features of the curve are the same for essentially all diatomics. So we're going to get a good qualitative idea that applies across a wide variety of diatomic molecules. The reduced mass of these 2 atoms is, in this particular case, in CO, is about 7 times the mass of hydrogen. In other words, about half of the average mass of the carbon and the oxygen. And that's about 10 to the 4th times if I bring this out, about 10 to the 4th times the mass of the hydrogen, M sub E, of the electron, Me. So this 10 to the 4th is a large parameter in this problem, or if you turn it around, it's a small parameter. And we'll see it arising in various contexts here. The small parameters are the mass ratio, electron mass divided by nuclear mass. Capital M here really means the reduced mass of the molecule, which is about 10 to the minus 4. The square root of it, which is about 10 to the minus 2, and the 4th root of it, which is about 10 to the minus 1. We'll see these small parameters appearing in the analysis. Okay. Now, given the fact that there's no analytical formula for that curve, we use a dimensional analysis to get at least order of magnitude estimates and what's involved with it. The physics of this is that the potential is determined by the interaction of the 2 electron clouds of the 2 atoms. And the dynamics of those 2 electron clouds is determined by, or it involves only 3 fundamental physical constants: the electron charge and the electron mass and H bar. Notably, the speed of light is not on the list because the electron dynamics is non-relativistic. Now, out of these 3 physical constants, EM and H bar, we can construct a unique distance, energy, velocity, frequency, any physical quantity you want, momentum, angular momentum, and so on, unique out of these 3 constants. So for example, the distance is H bar squared over ME squared. This is otherwise the Bohr radius, about 0.5 angstroms. The energy is ME to the 4th over H bar squared, which is 27 electron volts, which is about twice the it's exactly twice the ionization potential of the ground state of hydrogen, twice at 13.6 eV. The velocity is E squared over H bar, which happens to be alpha times C, where alpha is the speed of, alpha is the fine structure constant. And let me get the right pen here. Yeah, I do have the right pen. So the alpha is equal to E squared over H bar C. So if you multiply alpha times C, you get this velocity like that. That means this characteristic velocity V naught is basically the speed of light divided by 137, which is less than 1% the speed of light and essentially non-relativistic. The frequency is omega naught. Here it's me to the fourth over h bar cubed. This is basically the frequency of the orbiting of the electron in the ground state of hydrogen. In fact, all of these quantities here are the same as the quantities that occur in hydrogen. And the reason is that hydrogen has the same three fundamental constants, EM and H bar. So it determines the same scales for hydrogen as it does for the molecule. You plug in the numbers, you find that, so based on that account, you'd say that V0 ought to be as an order of magnitude about the same as K0, R0 ought to be as an order of magnitude about the same as A0. And in fact, they're off roughly by a factor of 2, which is not very bad actually for order of magnitude estimates. Okay, so I think this is where we left off at the end of the hour last time. All right. Now then, we've got a semi-quantitative idea of what this potential looks like. Let me switch to a new page and start writing some things down. Let's write down the Schrodinger equation here. I'll write down version 2 of the radial Schrodinger equation for this problem. It's minus h bar squared over twice the reduced mass, which I'm calling capital M, times f double prime. That's the version 2 radial wave function. Then we have the centrifugal potential L times L plus 1 h bar squared over 2. Again, it's the reduced mass that is to appear in the denominator, which I'm calling capital M here. And then we have plus V of R, which is the potential I just sketched, multiplying F of R is equal to the energy times F of R. So this is the radial Schrodinger equation for the diatomic molecule. Now let's start with the case L equals 0, which makes the centrifugal potential go away and just gives us the true potential V of R. In that case, what we have is a 1D Schrodinger equation with just V of R as the potential. So if I go back to it, you can see what's going to happen is you're going to get bound states in the bottom of this potential well. They're going to look like that, energy levels. And physically, what those are going to represent, well, classically, they represent the radial variable oscillating between turning points. What that means is that you've got the diatomic molecule and it's undergoing radial oscillations. As I say, it's vibrating like this, you know, I can do it like that. It's vibrating. So these are the quantized vibrations of the molecule. Now down near the bottom of this potential well, we can approximate it by a parabola. If I do that, just expand it out to second order in a Taylor series, I get a parabola that looks like that. It agrees with the true potential, you know, near the bottom of the well and deviates from it further away. So this parabola here has got some formula. It's got, in fact, the formula is this. It's going to be 1/2 capital M times the vibrational frequency, let me call it omega V squared, times R minus R naught squared. This is just setting it up as a harmonic oscillator potential with frequency omega V. And we need to put the reduced mass in here as the mass parameter, because that's what occurs in the kinetic energy over here. In this capital M is the reduced mass. All right, if we make that approximation, then at least down near the bottom, and assume that L is equal to 0, then at least down near the bottom of the well, we know what the energies are going to be. They're going to be N plus 1/2 times h bar omega V, for omega V being the vibrational frequency. But now the question is, what is the vibrational frequency? Is there a way to find out, or at least even to estimate it? And the answer is yes. What we do is we say that in order to estimate the vibrational frequency, we'll say that as you move up this parabola, this parabola attached to the bottom of the well, that to get to a distance where the curve crosses the R axis like this, meaning the potential goes to 0, we need to move out a distance which is comparable to the unit of distance, which is the Bohr radius. In other words, what we should expect is that as R gets comparable to, as R minus R naught, the distance from the bottom of the well gets comparable to A naught, we should expect the total potential V, which is minus V0 plus this harmonic part, to equal 0. And as an order of magnitude, that's probably okay. As far as the V0 is concerned, we can replace that by K0, which is what it is as an order of magnitude. And so plugging in then for the value of the harmonic part, which is 1/2 capital M omega V squared times R minus R naught squared, plugging this in and dropping the factor of 2 because we're just doing an order of magnitude estimate, what we get is M omega V squared times A naught squared is of the order of magnitude of K naught, or omega V is equal to K naught divided by capital M times omega times A naught squared, the square root of that. All right. Now then, if we go to our table here, and we get our K naught and we get our A naught, and we plug those values in terms of the fundamental constants, and then work this out, what you'll find is this becomes the square root of the mass ratio, small m over capital M, multiplying onto omega naught. Well, omega naught was this frequency down here. That's basically the hydrogen atom frequency. Omega naught, the hydrogen atom frequency, is basically the frequency. It's not basically, it is the frequency of the orbital motion of the hydrogen atom in the ground state, as I mentioned before. It's also, as an order of magnitude, the frequency of a photon, which is emitted in electronic transitions when you make change between electronic eigenstates. And this is also true in the molecule, that if you change the electronic state and emit a photon, it's going to be of a frequency of the order of magnitude of omega naught. Now, numerically, that works out to be something like in the ultraviolet range of frequencies. So these are ultraviolet photons, rather high energies by optical standards, and that's what this omega naught is. But we're finding that the vibrational frequency of the molecular vibrations is down by a factor of root m over m, which is about a factor of 100. So it's about 100 times smaller than omega naught. And so this cuts it down from ultraviolet frequencies, omega naught, down to vibrational frequencies, which are in the near infrared. Near infrared means reasonably near to the optical range like this, but they're in the infrared. So we see that here's where our small parameter occurs. And we see that there are at least two different energy scales then in the molecule. There's the electronic energy scale, which is like the same as in hydrogen, but there's a vibrational one, which is down by a factor of the square root of the mass ratio, roughly 100 numerically speaking. This is roughly 100, in fact, for, very roughly anyway, for almost all common diatomic molecules. So these numbers are actually reasonably uniform across the world of diatomic molecules. So vibrational transitions occur in the infrared. As far as the energy is concerned, I gave it to you here. Here it is. It's just harmonic oscillator energies, although of course that only applies near the bottom of the well. Something else you can do is to compute the number of vibrational bound states. If I go back to the well here, you ask how many will fit in this thing here, like this. They get closer together as you go up because it's not harmonic anymore. But again, by making just a simple estimate like I did before, it again turns into the mass ratio, but now upside down. It's the square root of big M over small m, which means it's about 100. So your typical diatomic molecule has something like roughly the order of 100 bound states before it dissociates and becomes broken apart and break the bond. All right, so this handles the case where L is equal to 0, where we could ignore the centrifugal potential. What happens if we include the centrifugal potential? Well, before I do that, I need to make a further statement about vibrational modes. Let's go back to this picture. If we took the ground vibrational state, it's going to be basically the ground state of a harmonic oscillator. So the wave function is going to be a little Gaussian wave packet looking like that. And this Gaussian wave packet has some width, and let me call it A sub V, meaning for A sub vibe for the vibrational width, the width of the vibrational ground state wave function. And what is that width? Well, I'll make a little box here, because if you go to standard harmonic oscillator formulas, like look in note 7, I think it was, you'll find that the length parameter of the harmonic oscillator wave functions is equal to the square root of h bar divided by m omega. That's using this general notation for a standard mechanical oscillator. For the present problem, we want to replace A by A vibe, the vibrational width, and that's going to be the square root of h bar divided by, instead of m the mass, we want to put the reduced mass here, which is capital M, and omega should be replaced by omega v. Well, we've got an estimate here for omega v. It's given up above right there. If we plug that in here and we work through the algebra, it's just simple algebra, combining things. What you'll find is you get the mass ratio, small m over big M, to the 1/4 power times A naught, which is the Bohr radius. So we get as an estimate then for our diatomic molecule that the vibrational ground state wave function is something like m over m to the 1/4 power is like 1/10. This is like 1/10 of A naught. It's basically 1/10 of the bond length, you see, if you estimate R0 as being A naught. And so what we see is that the vibrations of the molecule occupy a relatively small fraction of the bond length, namely roughly 10%, something like that. And so this is a justification, or it explains a justification for treating diatomic molecules as if they were rigid rotors. They are, to roughly speaking, they are rigid rotors. All right, now then, having done that, let's go back to the case where L is not equal to 0. Suppose we want to look at that. In that case, we have to take into account the centrifugal potential. Now, this has got a denominator r squared. But if r is close to the equilibrium radius r naught, we won't incur much error if we replace r squared just by r naught squared, which now makes this centrifugal potential essentially a constant. It doesn't depend on r at all. It depends on L, of course, but not on r. And by the way, notice that the moment of inertia, if I can write it down here, notice the moment of inertia is the reduced mass times r naught squared. So the centrifugal potential now has the form of L times L plus 1 h bar squared divided by twice the moment of inertia. And this is exactly the energy levels for a rigid rotor that we worked out on an intuitive basis earlier. So in the general case in which L is not equal to 0, we have energy levels that depend on two quantum numbers, n, which is a vibrational quantum number, and L. And it's given by minus V naught, which just references us to the bottom of the well, plus the harmonic oscillator energy, n plus a half h bar omega vibrational, and then plus the rotational energy, which is L plus 1 h bar squared divided by 2 capital M r naught squared. And this gives us a crude but actually reasonably accurate description of the energy levels of the molecule, vibrational and rotational terms here, as you see here, when the quantum numbers are not too large. It gives you a good qualitative picture of what the spectrum of a molecule looks like. Before I go on, I want to address the rotational part of this energy and do a calculation to see how does it compare to the other terms in the energy. In particular, how does it compare to the vibrational energy? To do that, let's consider let's call it delta E rotational. And delta E rotational will be just the difference in the rotational energy, let's say between L equals 0 and L equals 1. If so, the delta of L plus 1 is just 1. So what you get is h bar squared over 2m r naught squared. We'll kill the 2 because we're just doing order of magnitude estimates. We'll write as an order of magnitude estimate like that. And the r naught will replace by a naught to make an order of magnitude estimate. We know the rest of these things in here. And if we do that and we work through the algebra from our table, what we find is the delta E rotational is of the order of m over m to the 1/2 power of h bar omega vibrational, which in turn is of the order of m over m without any power on it at all, just m over m ratio of h bar omega naught, which is the energy for optical transitions. So this can also be written as h bar omega rotational is equal to that. So what we see is that the rotational energies are down by another factor of the square root of the mass ratio, basically about 100, in comparison to the vibrational frequencies, which in turn are down by a factor of 100 in comparison to the electronic frequencies. These are the three energy scales of a diatomic molecule, and it's basic to the physics of such molecules, these three scales. If I wanted to make a plot of the energy levels, will just draw a vertical energy axis like this. We can draw, first of all, somewhere here is 1/2 h bar omega vibrational is a vibrational ground state. Somewhere here is 3/2 h bar omega vibrational. That's the next one up. So on those are those energy levels there. But superimposed on that is the rotational part, and this gives a fine structure to these levels. So this is an L equals 0, and that's an L equals 0. The L equals 1 is a little bit above that. In fact, it's about 1% of the separation between the two. There's an L equals 1 there, and then there's an L equals 2 and an L equals 3, and so on. Now they get further apart as L increases. They're not equally spaced, but you get L equals 1, L equals 2, and so on. And the same thing up for the higher vibrational states. So this is gives you a rough picture then of what the energy spectrum looks like. At least it's the rotation and vibrational spectrum of a molecule. The fact that there's another factor of 100 in going from the vibrational energies to the rotational energies means that while the vibrational energies are in the near infrared, the rotational energies are in the far infrared or even in the microwave regime. And that's typically how it works for diatomic molecules. Now, one further comment about all this is that molecules are in the news these days because of greenhouse effect. It is especially carbon dioxide, as you know, but also water and methane to a certain extent, the greenhouse gases in the atmosphere strongly scatter infrared photons, which have a temperature of roughly 300 Kelvin, because that's the temperature of the Earth, basically, surface of the Earth. Those photons are the Earth emitting black body radiation out into space and trying to cool off. But those photons can't travel straight through the atmosphere because they're strongly scattered by the greenhouse gases. And the scattering takes place because of vibrational transitions in those molecules. It's mainly the triatomic and polyatomic molecules that do the scattering, not the oxygen and nitrogen, which are reasonably immune to scattering infrared photons. This is why they don't count as greenhouse gases. But anyway, that's the mechanism that goes on, and that's why these gases form a kind of a blanket around the Earth and hold the heat energy in. The radiation comes in from the sun at optical frequencies, which passes right through the Earth. Obviously, Earth's atmosphere is obviously mostly transparent at those frequencies, but it's not transparent at the infrared frequencies that are needed to get the heat back out into space. Okay, major problem for the future. Okay, that's all I wanted to say about molecules. It's the barest introduction to molecular physics that I think might be appropriate for an average physics student to know. So are there any questions about that? If not, I'm going to move on to the next topic, which is hydrogen. Yeah.
I have a quick question. Yeah. So,
yeah, sure.
So we did this for a diatomic molecule. So this is talking about basically rigid rotors. In order to analyze a triatomic molecule, what would you have to do? Everything gets so much more complicated, right?
Yeah. So in a diatomic, you have these vibrational modes. That's where the two atoms are moving in and out like this. I don't know if you can see me.
Yeah, I can.
That's the vibration. So in a triatomic, you can have not only vibrations, but you can also have bending modes.
Oh yeah.
And so CO2 actually is a linear molecule. It's got the two O's in the outsides and this carbon in the middle. So it has bending modes like that,
right?
As well as vibrational modes like that. So it's actually these bending and twisting modes are the main ones that scatter the infrared photons because they have the right lower frequency that allows that to happen.
I see.
But that's basically how it is.
Okay. Thanks.
Right. Okay. All right. You're going to have a career working on infrared spectroscopy of molecules. I'm not sure these days. It's kind of an old topic now, but maybe at one point you could anyway.
Well, actually, we sorry to but in undergrad we were interested in like absorption spectra of triatomic and higher molecules, and actually people haven't. The cross sections for these molecules haven't been worked out, or for most of them, in fact. So you can still make a career.
You mean experimentally measured or
theoretically or
calculated? Yeah,
theoretically worked out.
Well, okay, so there's a career for you. Okay.
Yeah, there you go.
All right. All right. All right. So I want to move on now to hydrogen atom, and I'll probably spend the rest of the hour talking about that. Before I start on hydrogen, I want to say something about atomic units. Atomic units are very useful in atomic physics, and they are basically units in which the electron charge, the electron mass, and Planck's constant h bar are all set equal to 1. And you may recognize that these are the same constants which are used in the cases of diatomic molecules in this dimensional analysis that we did. So to bring that back, here's our dimensional analysis, giving us the distance, energy, etc., all as functions of EM and H bar. So if we choose units so that E equals M equals H bar equals 1, which is atomic units, then A naught, the Bohr radius, just becomes equal to 1. K naught, which is twice the ionization potential of hydrogen, becomes equal to 1. That means that in atomic units, the ionization potential of hydrogen is equal to 1/2, or the ground state energy is minus 1/2. V naught, which is the unit of velocity, is alpha times c. So about velocities here, let's notice that where are we? Alpha is equal to E squared over H bar c. But if you take it into atomic units, the E and the H bar are both equal to 1, so it just becomes equal to 1 over C. So in atomic units, C is equal to 1 over alpha, which is equal to about 137. The speed of light is 137 in atomic units. So the unit of velocity is C over 137, which, as I say, is a relatively small velocity, but that's the unit. Frequency, likewise, here, it turns out the unit of frequency is the frequency of the orbital motion of the electron in the ground state of hydrogen. So that's the meaning of the units when we're working with atomic units. And it greatly simplifies calculations by getting rid of lots of constants you have to write down and where you have opportunities for making mistakes and pushing them around. All right. Anyway, that's the basic idea of atomic units. Now, before we talk about hydrogen atoms, let me mention that I'd also like to talk in the same breath, basically, about what we call hydrogen-like atoms. A hydrogen-like atom is an atom that has one electron, but the nucleus is not necessarily a proton or a hydrogen nucleus. For example, if we have singly ionized helium, that's the helium nucleus with one electron, and this is called hydrogen-like helium. Lithium atom with 2 electrons removed is a lithium nucleus with 1 electron. That's called hydrogen-like lithium. So the hydrogen-like atoms are all 1 electron atoms and can be treated by the same formalism. It just means that we're going to have a factor. So the nuclear charge E gets replaced by ZE when we're talking about hydrogen-like atoms. So let's treat them all together by doing that. All right, if we do that, then let's talk about the dynamical problem that we have. So we've got two particles now. I have a nucleus that has a charge plus ZE, and we've got an electron with a charge minus E. These are 2 charged particles. They are, of course, they are sources of electromagnetic fields, and they respond to electromagnetic fields also. So the dynamics of these 2 particles between themselves is something that has potentially a lot of complications to it. Nevertheless, what we'll do is make a certain approximation, which is pretty good when Z is not too small. Excuse me, when Z is not too large, it's a pretty good approximation. It's based on this. As we say that the nucleus is much heavier than the electron, so a frame attached to the nucleus is nearly an inertial frame. Or if we chose a genuine inertial frame, which was the center of mass of the 2 particles, then in that frame, the nucleus doesn't move very much. Well, if the nucleus really were stationary, then you could use electrostatics to get the Coulomb's law and so on, to get the electric fields and so on. So the potential then would be, if the nucleus were stationary, the potential would be ZE over R. This would mean that the electric field is equal to minus the gradient of the potential. Assuming it's really electrostatics, that would hold true. By the way, the electric field produced by the electron is not well described by electrostatics because the electron is moving. See, that's an issue. But for the nucleus, it's kind of okay. This means that the mechanical potential of the electron is the charge of the electron minus E times phi of R, and that's going to give us minus ZE squared over R, like so. That's what occurs in the Schrodinger equation. So this is what I'll call the electrostatic approximation. It is an approximation, or it's an electrostatic model, if you will, for the treatment of hydrogen-like atoms. It neglects a number of physical effects. It neglects the fact that the nucleus really is moving. So there is a question about retardation. Each particle doesn't actually know where the other particle is. It only knows where it was a certain time before, governed by the finite velocity of light. There's also magnetic effects. There's also effects of the radiation, emission, absorption of radiation. There's also effects of the interaction of the charged particles with the electromagnetic field. So there's all these complications. Nevertheless, the basic Coulomb model, or the electrostatic model, is a good first approximation, and that's what we do. That's what you did in your first course, but they probably didn't explain the electromagnetics of it very well, and I'm trying to do that now. All right, anyway, if we do this, then we end up with a Schrodinger equation, which you can write out. And I'll write it again in terms of version 2 because it's easier to write. This would be h bar squared over twice the reduced mass, which I'll call mu, times F double prime, plus the potential, which has a centrifugal part, LL plus 1 h bar squared over 2 mu r squared. Again, it's the reduced mass that occurs there, plus the potential, the true potential, which is minus ZE squared over R. times F of R, and that's equal to the energy times F of R. Okay. Now, this equation, this radial equation, has its own clutter of constants, and it's convenient to clean them up. But atomic units aren't the best way of doing it. Instead, we want to use what I'll call modified atomic units. So let me tell you what modified atomic units are. Modified atomic units are given by taking the square root of ZE squared is equal to the reduced mass is equal to h bar is equal to 1. In other words, they're obtained by atomic units by making the replacements E squared goes to ZE squared, and the true electron mass gets replaced by the reduced mass. Let's talk about the second replacement first. The reduced mass of the electron orbiting the nucleus is given by the harmonic mean. 1 over mu is given by 1 over m, the mass of the nucleus, plus 1 over the mass of the electron. Me means the same thing as m up here, so without the e means the same thing. And if the mass of the nucleus is much larger than the mass of the electron, which it always is, this means that the reduced mass is very close to the mass of the electron. Numerically, they're quite close to each other. I'll keep the distinction between them, but they're quite close. So this change from m goes to mu doesn't really change very much numerically. On the other hand, changing e squared goes to ze squared gives all of the units and modified atomic units a z dependence, and it's worthwhile paying attention to what they are. So for example, if I go back to my atomic unit table here, here's the A naught, this is our unit h bar squared over me squared. In modified atomic units, this A, let's call it A without a naught, this would be given by h bar squared divided by mu times ze squared. And this is, ignoring the difference between mu and m, this is approximately equal to the Bohr radius A naught divided by z. This is essentially a dimensional analysis we're doing here. And what it shows you is that hydrogen-like atoms have an effective Bohr radius, which is equal to the usual Bohr radius divided by the nuclear charge. So hydrogen-like uranium, for example, has an effective Bohr radius that's 92 times smaller than an ordinary hydrogen atom. Okay, I've made another table here, if I can find it, of the modified atomic units. And here's what they are. Again, these are the substitutions you make. So here's the unit of distance, as I just explained, it's A naught over Z. If you do it for the unit of energy, let's call it K without the naught. It goes as Z squared times the hydrogen value. This tells you that energies go as the square of Z compared to hydrogen-like energies. Velocity goes in proportion to Z times V0. Frequency goes like Z squared. The frequency of the electron in the ground state of hydrogen is already pretty fast. I mean, the time scale is sub-femtosecond. But if you wanted to crank that up to uranium, you see it increases by nearly 100 squared, nearly 10 to the 4th times faster. So it's really a high frequency. It's worth paying attention to the velocity formula here. In the case of hydrogen, V naught, as I pointed out, was the speed of light divided by 137, which qualifies it pretty well as being non-relativistic. But as Z increases, that gets to be less and less true. And if you go all the way to uranium or beyond, uranium Z is 92. So for uranium, you get Z alpha. Z alpha is 92 divided by 137, which is about 60-something%. So it means that in hydrogen like uranium, the electron is moving at about 2/3 the speed of light. And that in turn means that you really can't use the non-relativistic Schrodinger equation as a very good first approximation. And it also means that these assumptions that we were making earlier about the electrostatic model are actually not so valid anymore. So this,
I was just wondering, like, in practice, would we ever analyze a hydrogen like uranium atom? Is that something that we actually need to be worried about?
Well, people have done experiments on highly stripped down atoms like uranium. Yes, there have been experiments done on it because there's interest in the Lamb shift and so on. I'm not sure how recent they are. There's been within 20 years or something. It's not that long ago people did this. So that's one issue. Another issue is that even if you're talking about ordinary uranium, so it's got its full complement of electrons, the inner shell electrons or K shell electrons really are down there near the nucleus. And so they're really moving at 2/3 the speed of light. So some of the electrons are definitely relativistic, even in ordinary, fully clothed uranium, let's say. So the answer is yes, it is important. Heavy atoms need to be treated by relativistic quantum mechanics. All right, so this is a warning that in treating these hydrogen-like atoms, we can't let Z get to be too big without expecting our basic model to start to break down. All right, all that just comes from a dimensional analysis. All right, so that's basically the story of modified atomic units. If we go back to our, do I still have it on the screen here? Excuse me, I'm losing my voice. Here's our Schrodinger equation. If we introduce modified atomic units, then mu and ZE squared and H bar all go to 1. And so if I can go down here to make some space for it, the Schrodinger equation turns into this is -1/2 F double prime plus L times L plus 1 over 2R squared minus 1 over R times F of R is equal to E times F of R. So that's the radial Schrodinger equation we want to solve now in modified atomic units. You see how much easier it is to write now. All right, now the first thing to do in analyzing this equation is to sketch the potentials. So allow me to do that. Let's make a radius going out like this, and we'll sketch various potentials here. The true potential is -1 over R, so it does this. Goes down like this, is -1 over R. That's the true potential. The centrifugal potential is LL plus 1 over 2R squared. So that diverges, goes to plus infinity as R goes to 0. And then it dies off to 0 as R goes to infinity. So this is the LL plus 1 over 2R squared. That's that part of the potential. And the effective potential then is the sum of these two. So if the radius R is small, the centrifugal potential dominates. So the total potential for small r diverges, goes to plus infinity. But if R is large, then the Coulomb potential dominates because it dies off more slowly than the centrifugal potential. So that's negative, and that's what dominates at large radii. So again, there's a competition between these two curves. And if you add them together, what you get is a new curve, which I shall now draw. And it looks like this. It's going to be a function of radius. It comes to, so this is U of R now. It comes down like this, creates a well, goes out like this, and then asymptotes to 0 as R goes to infinity. So this is what we get. Now then, there's quite a few qualitative features you can see right away just by looking at this potential. In the first place, you expect to see bound states. Now this potential involved the centrifugal potential, which depends on L. So the nature of this well and how deep it is and its shape and so on also depends on L. So we generally expect these bound states to depend on L. We'll get back to that later on, but still there's a well, so there ought to be bound states. And in fact, we know there are. Hydrogen has bound states. In fact, as you know, it has an infinite number of them. We'll come back to that as well. Another point to make is you can see that there also are unbound states. This is the E equals 0 line right here. Because classically, for example, if I had a positive energy like this with a particle coming in, it would fall down this well, it would rise up and reach a turning point like this, and then it would come back out again. In other words, you got scattering solutions or positive energy solutions for all values of E greater than or equal to 0. There's a continuous spectrum up there of positive energies. At the same time, there are bound states of negative energy. Now, in this course, we're mainly going to concentrate on the bound states because they're easiest to analyze. But if you are dealing with this professionally, you have to worry about the unbound states as well. All right. And in particular, the bound states by themselves do not form a complete set. I want to mention that or emphasize that because you need to include the continuum states if you want a complete set of wave functions for hydrogen. All right, so those are the qualitative features. So let's concentrate on the bound states where the energy is negative. And if I go to my equation here, my Schrodinger equation, I'm now going to outline for you. You've no doubt been through this already in an undergraduate course, but I'm going to just outline the highlights of the procedure that's used in solving this equation. It's a somewhat standard techniques that work in important cases for being able to solve and find the eigenfunctions and eigenvalues differential equations of this type. They're 1D. They're sort of like 1D Schrodinger equation. This is a radial equation, of course, from a 3D problem, but it's essentially a 1D equation. There's some techniques that work in some cases, important cases. So I'm going to outline those techniques. So the first thing we do is we look at the asymptotic behavior of the solutions of this equation. That's to say, when R goes to infinity. When R gets very large, both the centrifugal potential and the true potential both go to 0. So as a first stab at this, let's just neglect both of those terms. And then we just have the radial kinetic energy and the total energy on the right-hand side. If we do that, the equation we get can be written this way as F double prime is equal to minus twice the energy times F. Now minus twice, the energy assumed is negative, so minus twice the energy is positive. What we do is let's make a substitution. Let's define, this turns out to be convenient later. I can't really motivate it now, but this later turns out convenient. Let's define a quantity n is equal to 1 over the square root of minus 2e. The notation n suggests that n is an integer, and in fact, later on it turns out to be an integer. But for now, we play dumb and imagine we don't know that, and so n just now is a real variable. It's just a convenient substitution for energy E. This means that E then is equal to minus 1 over 2n squared, which are then the negative energies you see. If we do this, then this right-hand side becomes 1 over n squared F, and it means that then F has the solution, F of R. It's not really a solution, it's only an asymptotic solution at large R's. R goes to infinity. It goes like e to the plus and minus R over n. Well, plus R over n is not allowed because that diverges exponentially. So you want to replace it by e to the minus R over n. That's going to be the only possible solution that can be allowed, is the behavior where it dies off exponentially as e to the minus R over n as R goes to infinity. Now this was obtained by neglecting the two potentials. So to account for them again, let's make an exact substitution. F of R is equal to new radial wave function G of R times e to the minus R over n. Let's do that substitution. And then we plug that back into the Schrodinger equation, radial Schrodinger equation here, and grind through the algebra to transform the equation from F into G. And if you do, you get something like this: a G prime plus some stuff multiplying G double prime plus some stuff multiplying G prime plus some stuff multiplying G equals 0. It turns into something like that. It's a linear, second order linear differential equation with non-constant coefficients. We solve this by the method of Frobenius, which is basically to look for a power series solution. As I say, we think of G as being analytic. Well, actually, we don't assume it's analytic. We allow for G to have a singularity at the origin. So here's what we do. We say G of R is equal to a power of R, let's call it R to the S, times a power series, which I'll write as K equals 0 to infinity of A0 times R, excuse me, A sub, let me do it right, A sub K times R to the K power. A power series with coefficients A sub K. And we'll assume that A sub 0 is non-zero. The R to the S takes care of the leading power. So the A sub 0 gets to be taken to be non-zero. So this allows you to take care of solutions which are a power series, therefore analytic, multiplied times something that might give you a singularity like 1 over the square root of R or something. This Frobenius method allows for that. If you then plug that into these equations, what you find is that the exponent S takes on two possible values. One of them is L plus 1 and the other one is minus L. This is for G of R, which is proportional to F of R. If you translate that into the version 1 radial wave function, this is equivalent to saying that R of R goes like either R to the L or else 1 over R to the L plus 1. And we saw this earlier as the two possible behaviors of the radial wave function near the origin. And of these, we rejected the 1 over R to the L plus 1 because it's non-physical. Likewise, here, using Frobenius method, we have to reject the S equals minus L. These exponents aren't the same because there's a factor of R transforming from capital R to F. In fact, F of R is equal to R times capital R. That's the transformation between the two versions of the radial wave function. In any case, we get S equals L plus 1 here, we find that. And then we substitute substituting that into the differential equation, we can solve for the coefficients A sub K of this power series. And if we do that, what we find is, let's call this power series P of R. I'll just call it P of R to give it a name. P just stands for power series. If you do that and you get those coefficients, then what you find is that P sub R goes as R goes to infinity. You find that P sub R goes as e to the 2R over n, unless something will fill in. If that power series goes as e to the 2R over n, then it more than cancels out the e to the minus R over n and the g of R and gives us a wave function that's not normalizable. So this is actually not allowed physically. We have to reject that. The unless is that unless the power series terminates. And if it terminates, then it becomes a polynomial. And P could also stand for polynomial as well as power series. So let's say we do that. And when you work through the details, then you get a polynomial Pn of a specific form. And the result can be summarized of all this algebra can be summarized in the following. It's convenient to introduce a modified radial variable, let me call it rho, which is 2R over n. And then what we have, and I'll write it in terms of the radial, the version 1 radial wave function, capital R. So capital R of R is equal to, there's a normalization constant, which I won't fill in. It takes some trouble to find that. Then we have rho to the L. Then we have e to the minus rho over 2. That's the asymptotic behavior we stripped off. And then there's a polynomial in L, which is a so-called Laguerre polynomial. It has two indices, of which one is 2L plus 1 and the other one is n minus L minus 1 of rho. This is just how it works out using the details of Laguerre polynomials. It's worthwhile mentioning, however, that this is a polynomial of degree equal to the lower index, which is n minus L minus 1. And this polynomial terminates, this power series terminates as a polynomial, if n, which started out as being a continuous, possibly a continuous variable, as I said, we had an open mind about it. Turns out it has to be an integer, but not just any integer. It has to equal the values L plus 1, L plus 2, and going all the way out to infinity from there. In other words, there's a starting point, which is L plus 1. L, remember, is a parameter of the radial Schrodinger equation. Then it takes on the values 0, 1, 2, 3, and so on, the usual quantum numbers for angular momentum. So the n starts with 1 or 2 or 3 or whatever, depending on the value of L. All right. So this polynomial of degree n minus L minus 1 means it's always of a non-zero degree. And in particular, when n equals L plus 1, which is the lowest value of L, this polynomial is just of degree 0, which just means it's a constant. All right. Now, then the radial wave function then depends on L. It has to depend, radial wave functions always have to depend on L because the radial wave equation depends on L. But it also depends on n, which we now see is the sequencing number of the energy levels. In fact, the energy levels are given by the same formula that I wrote down earlier, except when I wrote this down, we were thinking that n might be a continuous variable for all we knew. Turns out now it's an integer. So the formula still holds, except n is an integer. So it's minus 1 over 2n squared, and we might as well put an n index on that. All right. And in this manner, we have derived the energy levels and the wave functions for the hydrogen atom. Now, this ought to be a review of what you did in undergraduate school. So let me pause here and see if there's any questions about it. This is a fairly standard method that works for a number of different equations of this type. You can use it for the harmonic oscillators, for the YLMs. You can use it for other problems as well. D matrices can be handled this way. All right. If not, then I'll proceed. That's the summary of the solutions. Now, the total wave function in 3 dimensions, psi, n, L, and m, depends on all 3 quantum numbers of r, theta, and phi, is the radial wave function Rn L of R times the YLM of theta and phi. That came from the elimination of the angular variables that we did earlier. The RNLs, as I keep saying, L is a parameter of the radial wave function, n sequences the energy levels. This is the radial wave function is essentially a 1D wave equation. And so these radial wave functions are orthogonal to one another for different values of n, but for the same value of L. What that means is there's an orthogonality relation, the integral from 0 to infinity of r squared dr times r n L of r times r n prime L of r is equal to Kronecker delta n n prime. This assumes that you've normalized the wave functions. But if you have, then you have this. I could put a star in this if I want to, but these wave functions are normally real, so you don't need that. So you get an orthonormality between different values of n, but the same value of L. And that's because these are just 1D eigenfunctions of a given 1D equation. You don't get orthonormality amongst the RNLs for different values of L because those are different radial wave equations. Those, in fact, are not orthogonal to one another. On the other hand, if you take the full three-dimensional wave equation, you do get orthonormality among different values of L because the YLMs force that. So the psi NLMs, scalar product of n prime, L prime, M prime, gives you a complete collection of Kronecker deltas, n prime, L prime, and M prime. But the LL prime Kronecker delta is forced by the YLMs, and then the NN prime Kronecker delta comes from this integral, this radial integral. So that's a few comments about the orthonormality relations. All right, now let's plot the solutions. Let's make a diagram of the energy levels. So we want a vertical axis that contains energy. Like this. And I'm going to put the level E equals 0 up at the top because the bound states are all have negative energy. So we're interested in what happens below E equals 0. There's a continuum up above, but anyway, we'll look at what we know right now. Let me bring this down some. So I can start drawing horizontal lines here to represent energy levels, but because there's a different radial wave equation for each different value of L, let me bring this over here, we can organize these in columns by the different values of L. So let's have one column for L equals 0, another for L equals 1, another for L equals 2, L equals 3, and so on, going out this way. And if we do this, in effect, we create a two-dimensional diagram with energy being vertical and angular momentum being horizontal. This is what's normally done in these types of diagrams. Let's look at it. Let's look at L equals 0 first. For the L equals 0 case, the n values run from 1, 2, 3, and so on like this. And the energy levels, I'll remind you, in modified atomic units are -1/2n squared. So the ground state is n equals 1. Let's put it down here. I should have left more room here. Here's the ground state right there. This has an energy of a -1/2 because it just setting n equals 1. The next value of n is n equals 2. The energy level is -1/2 times 2 squared makes it -1/8, and it makes it actually 3/4 of the way between here and the E equals 0. The equals 0 is the threshold for the continuum. You see above this value, you've got continuum states, continuous spectrum going up here in each of these columns, like so. In any case, we move 3/4 of the way up there, and we get, best I can sketch it here. We have the n equals 2, and this has an energy of -1/2 times 2 squared. Somewhat above that is n equals 3. It's got an energy of -1/2 times 3 squared. And there's an n equals 4 at -1/2 times 4 squared, and so on. And then there's an infinite number of energy levels that accumulate up like this until you reach the continuum at E equals 0. Now, if I take the L equals 1, the leading value of n here is n equals L minus, n equals L plus 1, which means it starts with n equals 2. So in the L equals 1 column, the n equals 2 level is the first one, and all the others occur like there as well. The energies depend only on the n quantum number and not on L. So this is the same level as in the L equals 0 column, but it just starts higher up. For L equals 2, it starts at n equals 2 and goes on up like this. For L equals 3, it starts at, for L equals 2, it starts at n equals 3 and goes up. For L equals 3, it starts at n equals 4 and goes on up like this. So you get you get an energy level diagram for hydrogen, which looks like this. These levels are given what's called spectroscopic notation. In the first place, the angular momentum values 0, 1, 2, 3, and so on are associated with code numbers, code letters, which are SPDF for the first four. They just have historical significance and really don't mean anything anymore. Followed by the F, you just run through the alphabet. So it goes SPDF, G, H, I, and so on. And at some level, you're going to start running into P's and D's, but that's so far out that nobody ever encounters it. Anyway, you have these code letters, and the angular momenta are identified by code letters you simply have to know. The levels themselves are given in the form of NL, but coded where the L is replaced by the code letter. So for example, the N equals 1, L equals 0 state is denoted 1S. And that's this state right here is 1S. In fact, this entire column is 1S because this is the S column. So that's the 2S state, that's the 3S state, the 4S, and so on. This is the 2P, the 3P, the 4P, and so on. This is the 4P, let's see, excuse me. This is the not the 4P, this is the 3S3P. Oh yeah, this is the 3D, 4D. This is the 4F, and so on like that. That's how these levels go. All right. Now, so this is your basic energy level diagram in hydrogen, along with the spectroscopic notation for the levels. Let me say something about the degeneracies of these levels. If you're just looking at the radial equation itself, that's to say, looking at are there linearly independent radial wave functions for, a given L, but different values of N, the same energy. The answer is no, because those are 1D wave equations. I explained this earlier. They're 1D wave equations with the right boundary conditions. That means that regarded as 1D equations, their levels are non-degenerate. This applies even in the continuum. However, to get the 3D wave function, it needs to be multiplied by the YLMs, and the energy levels don't depend on the magnetic quantum number. So those are therefore are 2L plus 1-fold degenerate because of the number of M values. So the L equals 0 levels are 1-fold degenerate because of the M values. L equals 1 are 3-fold. The 2 are 5-fold degenerate, and so on. It's 2L plus 1 is the number in question. It's 7 here. So these levels I've drawn here are actually overlying multiply degenerate levels, at least in the L equals 1 and columns moving to the right. So that's some comments about degeneracy. Here's another important comment about degeneracy. It's important for the sake of understanding hydrogen. I think a lot of people don't pay attention to this enough. If you have any central force problem, the radial wave equation, as I keep saying, is parameterized by L. So in effect, there's a different radial wave equation for each different value of L. For any central force potential you want, you can make a diagram like this with energy vertical and L going horizontal with a series of columns one after the other. You can always do that for any central force problem. However, because the radial wave equation is different for each one of these columns, in effect, you're solving a collection of different one-dimensional Schrodinger equations. And in general, there's no reason why the energy levels in one of these columns should be the same as energy levels in another column. They're in effect like random numbers that are thrown down on the energy axis for each one of these columns. And so for a randomly chosen central force potential, it's unlikely, in fact, it's extremely unlikely that there's any coincidence between levels amongst different columns. Now, the levels could come very close together, but to have them come exactly on top of one another is, as I say, is very unlikely. Nevertheless, in hydrogen, what we see here is the levels are exactly on top of one another, moving across these horizontal lines. And that's because in hydrogen, the energy levels depend only on the quantum number N and not on the quantum number L. They're independent of the angular momentum quantum number. And that is something that is not to be expected for other central force problems. As I say, it's not obvious why it should happen even in hydrogen. In general, you don't expect that, and it doesn't happen generally. It didn't happen for the diatomic molecule, by the way, if you recall that fine structure of the rotational structure superimposed on the vibrational structure I don't know if I still have the diagram here, but I'm not sure I have it anymore, but that was the case in which the energy levels definitely depended on both N and L. Now, so the question then is, why is there this extra degeneracy that goes beyond what happens in general central force problems? Why is there extra degeneracy in hydrogen? The 2L plus 1-fold degeneracy that applies in the different L columns is due to rotational invariance. That's because the energy levels don't depend on the magnetic quantum number. And the reason they don't is because that's the quantum number of the operator LZ, which is the projection of the angular momentum onto the Z axis. Now, if the system is rotationally invariant, then you can rotate the system and it won't change the energy. But what it will do is change the projection of the angular momentum onto the Z axis. So therefore, the energy can't depend on the value of that projection, and it doesn't. That's the reason for that 2L plus 1-fold degeneracy. But that applies to all central force problems. Hydrogen has extra degeneracy. Where did that come from? The answer is that hydrogen also has extra symmetry. Degeneracies are related to symmetry. There always are a sign of symmetry. And in fact, this is a clue in the analysis of sometimes experimental data. Experimental data produces levels that are degenerate or nearly degenerate. Typically they're nearly degenerate if they are close together. This is a clue that there's that whatever the underlying Hamiltonian is that there's a symmetry that's forcing this degeneracy. This has played an important role historically in the history of physics. For example, the fact that the proton and the neutron have very nearly the same mass. One is 938 and one's 939 MeV. I think it's, to within 1 part in 1,000, pretty close. Why is it so close? Well, the logical explanation is that it's forced by a symmetry. It's not an exact symmetry. It's broken by some small effect. That's what caused the splitting. But there ought to be some symmetry there that caused the degeneracy. And in fact, this is the clue that led to the theory initially of isospin, and then later the quark theory, the SU3 symmetry theory, which is now the foundations of strong interaction physics. All right. So anyway, my main point here is that degeneracies are caused by symmetries. So the extra symmetry in hydrogen is not due to rotations. It's due to the fact that whereas all central force problems have SO3 symmetry, that's the rotations in ordinary three-dimensional space of the potential, which depends only on the radius r. In the case of hydrogen, there's actually an SO4 symmetry. This is in the case of the hydrogen atom. And SO4 is the group of rotations, orthogonal transformations in a four-dimensional space. And the way it works on hydrogen is that these, of course, are not rotations of the position of the electron, because that's only in 3 dimensions. Rather, it involves rotations that engage both the position and the momentum of the electron in a somewhat complicated way. But it's related to the existence of what's called the Runge-Lenz vector, sometimes denoted by A, which is a vector of conserved quantities in the hydrogen atom. It's also in the classical Coulomb-Kepler problem. It's also in this classical Runge-Lenz vector as well. In any case, taken together with the angular momentum, this forms a set of 6 conserved quantities in hydrogen, which taken together generate an SO4 group. At least it does so for the bound states. Whereas for a randomly chosen central force potential, you only have the orbital angular momentum as generators of symmetry, which makes the SO3. Now, I'm not going to go into that in any detail. You can read about it in Schiff's book on quantum mechanics if you want to learn more about it. It's an interesting story about hydrogen, but it's the explanation for this degeneracy in hydrogen, this extra degeneracy. Now then, on the other hand, given what I've said, it follows that by the way, are there any questions about that before I go on? Because this is one of the most interesting things about hydrogen, actually. Yes.
Does the degeneracy go away if you consider relativistic effects, or no?
Yeah, I think I prefer not to answer that question because it'll enhance your suspense and the sense of seeing the plot develop as we do this course. because we're going to consider relativistic effects, and then you can see. It's a very interesting story.
Okay.
It's actually a very interesting story. The yeah, okay. Now, by the way, the way I described solving just a moment ago, the radial wave equation for hydrogen, I use this method of Frobenius and everything, working through differential equation theory. And you may have noticed that that's rather different than what we did with the harmonic oscillator, where we use Dirac's algebraic techniques. And also in the case of the YLMs, we used algebraic techniques. It can all be done by raising and lowering operators. So you might be wondering, those problems, by the way, can also be done by Frobenius and differential equations if you want to do it that way. So why did I switch over to differential equations here when earlier I was using raising and lowering operators? The reason is that although this problem, the hydrogen atom, can be done with algebraic techniques, it's too complicated, it's too technical for the purposes of this course. It would take us too far afield, and I'm not sure you'd like it that much if I did it. So this is the easiest way of getting through the material, but it's worthwhile noting that it can be done. I'll give you a little historical note on this as well. There was a brief period in the history of quantum mechanics in which what was known as matrix mechanics, or what is known as matrix mechanics, was known, invented by Heisenberg, but Schrödinger had not yet come out with his differential equation. And using matrix mechanics, Heisenberg and especially Pauli solved some important problems, including the harmonic oscillator and the hydrogen atom. It was Pauli that did the hydrogen atom. Pauli had done his PhD dissertation using the old quantum theory, which we haven't talked about much, using the old quantum theory. I'm sorry that light keeps blinking on and off. It's actually the software which is trying to get the light level right, and it can't make up its mind about it. Excuse me just a second. I'm gonna try an experiment, see if this will help. I'm going to turn that light off and see if it makes a difference. Let's see if that helps. Maybe not. Anyway, so back to the history. Yeah, so Pauli used the old quantum theory to analyze the H2 plus ion. This is a hydrogen molecule in which one electron has been removed, so it's one electron orbiting two protons. And he analyzed that through the old quantum theory. And this involved going through an awful lot of Poisson brackets and working out classical commutation relations amongst observables. So when real quantum mechanics in the form of matrix mechanics came along, he knew just what to do in terms of computing commutators and things like that to algebraically solve the hydrogen atom. And it involved using the Runge lens vector and the orbital angular momentum as a collection of 6 observables and running through them, much like we did with, in a simpler case, with just orbital angular momentum with the case of the YLMs. And from that, he was able to derive the Bohr and ultimately Balmer and Rydberg spectrum of hydrogen formulas for it. This was a great accomplishment, but within a few months, Schrödinger had solved his equation using differential equation, using the techniques I just described to get the same answer. And after that, everyone was happy to drop the algebraic techniques. All right, anyway, that's a bit of history on this. In any case, in view of what I've said, it follows that if we took the hydrogen atom potential, the Coulomb potential, which has this special symmetry, and we perturbed it in such a way as to maintain a central force potential, but to change it from a Coulomb potential to something else, maybe just a small perturbation, then it ought to break the degeneracy in the L values across the columns. And what I'd like to do in the rest of this time that I've got is to give you 2 physically interesting ways of doing that. And it turns out that's true, and that's what happens. So one of the ways of doing this is what's called the volume effect. And I'm going to just basically outline the volume effect without going into details, because I'm going to give it to you as a homework problem later on when we do perturbation theory. But the volume effect concerns the fact that in a hydrogen-like atom, the electrostatic potential V of R is not really a Coulomb potential because of the fact that the nucleus is not a point charge, but it rather has a finite radius. If we take ordinary hydrogen, in which the proton is the radius, the proton is a particle you can think of it as having a finite radius, and let's call it RP for proton. It's of the order of about 10 to the minus 13 centimeters. It's a little bit more than that, maybe twice that or something, but it's like 10 to the minus 13 centimeters, which makes it roughly something like 50,000 times smaller, 50,000 times smaller than less than A naught, the Bohr radius. So it means that the proton occupies an extremely small, if you get the volume, you cube this factor, you raise it to the third power. It means the proton occupies an extremely small volume, part of the volume of the hydrogen atom. Similarly for other nuclei. Now, when you combine nuclei together, nucleons together to get compound nuclei, that means protons and neutrons, they, to a good approximation, they just pack like hard spheres. So for helium, you have 2 protons and 2 neutrons, and they pack together like this, pretty much as hard spheres. If we let A stand for the total number of nucleons, which is the number of neutrons plus the number of protons, N plus Z in standard nuclear notation, so A is the total number of nucleons, it means that the radius of the nucleus scales with, it's basically equal to this radius of the proton multiplied by A to the 1/3 power. And this is a crude but quite a useful rule for understanding the size of the nucleus. If you have uranium in which the A is equal to 238 in the usual isotope like this, A to the 1/3 power is roughly equal to 6. So it means that the uranium nucleus is roughly 6 times the size, 6 times the radius of a hydrogen nucleus. It's not that much. I mean, the size, it's bigger, but it's not that much bigger, all things considered. So nuclei are really small compared to the size of an atom. That's the first lesson here. Now then, on the other hand, they do have a finite size. And so if we take the Coulomb potential here, let me sketch it here. V of R is a function of R. There's some radius, let me call it A here, which is the radius of the nucleus. Let's call this radius R equals A here, like this. And if I sketch the 1 over R potential, it's really only 1 over R outside the diameter of the nucleus. Outside the nucleus, the charge density falls to 0 rapidly, and you just get the external field, which is by Gauss's law just determined by the charge inside. But inside the nucleus, the potential rounds off and actually becomes softer and actually goes to a finite value at V equals 0, like this, instead of continuing on down to negative infinity, as Coulomb would predict. And so what that means is there's a difference between the true potential V and the nominal Coulomb potential, which is used in the usual solution of the hydrogen atom. The true potential is above the potential we use in the derivation. And so what you can see is that the effect of this is a perturbation. The effect of this perturbation is to raise the energy levels of the atom. Now, on the other hand, as I've explained previously, the radial wave function Rnl of R behaves as R to the L power as R goes to 0. And the size of the nucleus, this A, as I just explained here, this A is much, much less than A naught, which is the Bohr radius. This is the A of the nucleus. It's much less than the Bohr radius, the size of the atom, by a factor of 10 to the 4th or 10 to the 5th. So although I drew it exaggerated here, this region over which the 2 potentials differ is spatially very, very small. Also, as the angular momentum, quantum number L increases, the radial wave function lies down more and more flat near R equals 0. In fact, it's only the L equals 0 wave function that really has any appreciable non-zero value in this very small region. The higher values of L have much, much smaller values of the wave function. And so the result is that it's mainly the L equals 0, that is to say the S wave states, which are affected by by this perturbation what's called the volume effect. It's mainly the S energy levels are raised, and most of the others, the P, D, F, and so on, are not affected very much. So it's a small effect numerically, at least in hydrogen, it's quite a small effect. But the effect is mainly to cause the S levels to raise up a little bit. And you can see that what that does is it breaks the L degeneracy between the different columns here. And that's exactly what we would have expected on the basis of what I mentioned earlier about the broken symmetry. All right.
Is this effect only dependent on L, or is it also dependent on N?
No, the energy shift depends on N, but the energy shift it mainly depends on L, because it's essentially zero for these higher L states, because the wave function is nearly zero inside the nucleus if L is greater than zero. It's only the S waves that have an appreciable value of the radial wave function inside the nucleus. Now, given that fact, when you do the calculation, the answer is definitely going to depend on the N value. Yes, that's right. But the numbers you get are essentially infinity compared to the numbers you get in the P or the D columns.
Right, right.
Okay. So the effect is far and away strongest for the S waves. All right, so that's the volume effect. By the way, the volume effect is almost it's very small for hydrogen. Although it's played some role in recent research having to do with I didn't prepare this before coming in tonight, but it was like a year ago, it was in the news. People were using the volume effect to compare predictions of quantum electrodynamics with observations, and one had to take the volume effect into account. Oh yes, now it's coming back to me. It has to do with the question of the radius of the proton. There was a significant disagreement in the radius of the proton coming from different experimental techniques, and one of them had to do with the volume effect. I think that discrepancy finally got resolved, but I'm not quite sure the status of that question right now. By the way, this extreme ratio that I spoke of being, 10 to the fifth or something for the case of hydrogen, that gets a lot better if you go to high Z atoms, because as I explained earlier, the radius of the atom scales is 1/Z. And in the case of uranium, the atom is 100 times smaller radius than it is for hydrogen. And the nucleus is correspondingly somewhat larger, not that much, but a factor of 6. So it adds up, and the result is that the volume effect is much more significant for a nucleus like uranium than it is for hydrogen by quite a bit. Fractionally speaking, it's quite a bit more. It's actually, you need to take it into account. Another simple remark too is that if you had, I think you can see that if you had really good data on the volume effect, it would give you information about the distribution of charge inside the nucleus. Okay, it was a question.
Does the fact that the nucleus has non-zero volume also affect the electron by essentially providing like a hard wall at the center of the atom?
Oh, interesting question. You would think that, wouldn't you? You think the electron couldn't penetrate into the nucleus, right? Because there's like a wall or something to prevent it. But the electron doesn't feel the strong interaction. It's a lepton. What the electron feels is the electromagnetic interaction. And so the answer is that it's free to enter the nucleus and wander around inside there, although it's affected by the distribution of charge inside the nucleus. Now, the charge inside the nucleus is positive charge and repels the electron. But that's all electromagnetic effect or electrostatic. It doesn't have anything to do with the strong interaction, which the electron does not feel. It's interesting.
Yeah, thank you.
So does that mean that to perform more precise calculations, we would have to modify what the potential near the nucleus looks like?
Yeah, you just make it look like that.
And then we would have to recalculate what the electron density
you'd
looks like.
You'd have to take into account what the charge distribution is inside the nucleus to know what that curve is, you see. Or what I was trying to say a minute ago, if you don't know what that charge distribution is, then you could use the experimental data to get, in theory, to get a handle on what the curve is. Turn it around, in other words.
Okay.
And people do that. They do that for, for exploring the structure, the internal structure of the nuclei. All right, there's one more example of this breaking of this extra degeneracy in hydrogen, and this has to do with alkali atoms. alkali atoms. So let's take the case of sodium, Na. Sodium has a Z equals 11. And a sodium atom can be thought of as a core, which consists of the nucleus plus 10 electrons, the core electrons, and then the single electron moving out here, which is the valence electron. So in sodium, as in other alkalis, there is a model that can be used in which we take the atomic core consisting of the nucleus and the core electrons and treat it as if it's a spherically symmetric distribution of charge in which the single valence electron is orbiting. So to do this, let's introduce what I'll call the Z effective as a function of radius. So the Z effective times E, let's write it this way, is by definition is the amount of charge, the total amount of charge inside the radius R. I'll just write it in words because it's easier to say it that way, what it means. If this is the case, then the Z effective of R, we can make some statements about it, is that if you approach the nucleus, if you take a sphere of radius R and let it shrink down towards the nucleus so that as R goes to 0, then Z effective is equal to Z, which is in the case of sodium, that's 11, is the total unscreened charge of the nucleus as R goes to 0. But as R goes to infinity, you get the charge of the nucleus minus the charge of the core electrons, which just leaves one left over. So the Z effective goes like this, you see, in these two limits. Now, by Gauss's law, the electric field at a given radius R, assuming it's radial, by Gauss's law, this is equal to the Z effective of R divided by R squared, because the charge outside radius R doesn't contribute, as you know from using Gauss's law. And this means that the potential phi of R is given by the integral from R to infinity of Z effective of R prime over R prime squared dr prime, like so. Actually, I didn't say this quite right. I should multiply by the charge, the total charge is Z effective times E, that's the charge. And then this needs to be multiplied by E here as well. And so the potential V of R is basically the same integral with a minus sign because the charge of electrons minus E, R to infinity, Z effective of R prime times E squared divided by R prime squared dr prime. In any case, we now get a potential, a spherically symmetric potential V of R, which can be used in the radial Schrodinger equation for this model of the alkali. Now, the qualitative behavior of this potential V of R is not so dissimilar from what happens in a Coulomb potential. It basically does this kind of a thing. It goes to 0 like at large distances, it goes to 0 like 1 over R, because if you're well outside the core, there's essentially only one charge shining through here. It looks just like the hydrogen potential. So it goes like 1 over R over here. But down at small radii, what you're seeing is the unscreened charge of the nucleus. So it's closer to being like Z over R down there. This is E squared over R, Z E squared over R. That's what comes with a minus sign, of course, minus this. So although it has the same kinds of asymptotes, the behavior at the two ends is quite different than a Coulomb potential that you'd have for any fixed value of Z, whether it's Z equals 1 or Z equals 11 or the average of the two. It's not gonna fit well over the whole range. And what that means is that any purely Coulomb potential is not a very good approximation to the true potential. So the breaking of this symmetry, this Coulomb symmetry, ought to be rather strong in the case of an atom like sodium. And indeed it is, as you will see if I draw you an energy level diagram of sodium, it looks something like this. So there's a continuum threshold up above, and there's the columns S, P, D, and so on. I'll just concentrate on some of the S stuff. So there's a 3S level here, which is the ground state. The 3S level, the ground state is a 3S rather than a 1S because the N equals 1 and N equals 2 electrons shells are filled. That's the core. And so the first valence state available to the valence electron is 3S. Anyway, in hydrogen, the 3S would be degenerate with the 3P, but in sodium, the 3P is up here like that. And then there's a Yeah, there's a 3S and a 3P, and there's a 3D up here too, like so. SPDF, there's an F out here as well. There's also a 4S. I forget whether the 4S is above or below the 3P. I think it's slightly above. There's a 4S, a 4P, and a 4D, and so on, and a 4F that looks something like this. This is very roughly what this is. In sodium, this splitting between the 3P and 3S, which would be 0 in hydrogen, is quite large. It's actually an optical transition. This is the sodium D line, which makes sodium flames yellow, which you no doubt did the flame test in your chemistry class. And that's what you see. It's also, it makes burning wood fires yellow. There's enough sodium in there to do it. But my main point is that this being a yellow photon means it's an optical transition, and it has an energy comparable to the transitions between states in hydrogen who have different values of N. It's not a small perturbation. On the other hand, as the angular momentum value increases, the splitting between the different N quantum numbers gets less and less. For example, the 4D and 4F are nearly degenerate with each other. It's starting to look like hydrogen again. Why is that? The reason is that if the angular momentum L is large, then it means that the orbit is nearly a circular orbit. And if I have an valence electron out here moving in a circular orbit, so in the first place, if the principal quantum number is large, it means the orbit gets larger. If L is also large, it means the orbit is a circle, like this. And if both of those are the case, then that orbit stays well away from the core, and the electron mainly just sees a hydrogen potential, 1/r. And so not only are these levels like the 4D and 4F nearly the same as in hydrogen, but they're also nearly degenerate with one another for the same reason. On the other hand, if the principal quantum number is large, so the maximum, the aphelion, if you will, in solar system language, if that's a large distance, so that you're well outside the core, but the angular momentum is small, then the orbit is like a little ellipse. It goes down like this and penetrates the core. So even if N is large, but L is small, you're going to get significant effects from the core. And that's why, for example, the 4S is significantly below the 4P, or the 3D is significantly above the 3S. That's these differences here. In any case, all of this can be understood in terms of this simple core model. There's a simple a screened core model, which is quite useful for alkali atoms. Well, I'm sorry, I'm afraid I ran over time, but that finishes everything I wanted to say about hydrogen. So let me stop now and ask if there's any questions. All right, if there's no questions, I shall stop screen share. And then I shall stop recording.